Welcome, ladies and gentlemen. And so we know that there are different ways of representing points in the coordinate plane. We have a regular Cartesian XY rectangular grid, but we also have our polar grid. And so instead of plotting points x comma y in the Cartesian grid, we can locate points using the polar grid by changing that point into what ordered pair, right? What's our ordered pair now? Marissa?
R and then theta.
R comma theta. Thank you. Raise your hand if you had R comma theta. And what does the R stand for? What's the R referring to? Grace?
The magnitude.
Yeah, the magnitude away from the origin. R, the magnitude from the origin. Thank you. And what is then does the theta represent? Courtney?
Direction.
Yeah, the direction in which you're going to go, right? That magnitude before plotting your point. Awesome, thank you. In general, for what function values must we be particularly careful with when plotting in the polar plane? So we ran into this a little bit on Thursday's discussion. So what function values must we be particularly careful with when plotting in the polar plane? What'd you have for that one? Riley?
Negative magnitudes.
Yeah, negative magnitudes. Negative R values. So why do we have to be careful with those negative magnitudes or those negative R values? Kobe?
Because they go like opposite direction.
Yeah, those negative magnitude, those negative R values can still be plotted. We'll just go in the opposite direction. So let's go ahead and practice. Here we go, and I try my best to do the color coding. So I was making this from home, and I'm thinking, okay, now what are the 4 colors on my marker tray? Okay, so we've got blue. Let's see if this works out. Magnitude of 3 in the direction of 7 pi over 6 radians. We can totally do that. All right. Let's go 7 pi over 6 would be right here. And we're going to go 3. 1, 2, 3. So how does that look for point A? How did I do? Awesome. So we're going to get point A. Point A. Great. B, green. I can do this. B, green. The earth is our mother. She will take care of us. No, you guys don't know that? Oh, okay. So 2 in the 5 pi over 3 direction. So 5 pi over 3. And we're going to go a magnitude of 2. So it looks like right here, point B. Raise your hand if you have point B. You guys have that? Great. C in black. Here we have a chance to practice our negative magnitude. We're going to go negative 3 in the 3 pi over 4 direction. So here we go. Pi over 4, 2 pi over 4, 3 pi over 4. But we're going to go in the negative direction. So we're really going over here at 7 pi over 4. 1, 2, 3. Can we share? Can I get that? Raise your hand if you had C correctly plotted. So you did the negative magnitude. Great job. And lastly, negative 4 comma 0. So this is not the regular Cartesian coordinate plane. That 0 is not a y coordinate, right? That 0 is the direction. So how can we go negative 4 in the 0 direction? Where's that going to be? Danny?
It's going to be positive 4 in the pi direction.
Absolutely. So here we go in the pi direction. We're going to go positive 4, 1, 2, bless you, 3, 4, and that's red. And gosh darn it, I didn't make it all the way with the colors. It break my heart. So who had D correctly? D correctly? Great work, you guys. What questions do you guys have on your Bellwork? So we pulled up our polar coordinate prior knowledge. We're ready to rock and roll for today's discussion. More polar graphing, but first, let's go ahead and take care of our assignment check. So I'll pause the recording, and we'll get you credit for your OTL number 4. Thank you for your help. Let's go ahead and reconnect with our function, right, in the xy coordinate plane and how we can use that to sketch a graph of the polar equation in the polar plane. So here we go. Consider our original function f of x given by 3 plus 2 sine of x. And this is a new one. We can go ahead and specify our scale. On the x-axis, I'll go ahead and do a complete cycle, pi over 2. Pi, 3 pi over 2, 2 pi. And if we went 1, 2, 3, 4, 5, it looks like our period of this trigonometric sine function is unchanged, so still 2 pi units to complete one full cycle, but we do have an amplitude of 2 and a center line of y equals 3. So let's go ahead and add that in. Our center line and our amplitude of 2 means that when we start our center line max, center line min, center line cycle, we're going to go not up 1 unit but up 2 units to get to that max. So at pi over 2, our maximum now is at a y coordinate of 5, back to center line. A minimum is going to be down at y equals 1, and then back to center line. Let's go ahead and make a nice smooth sine function, no corners, no kinks. Forever, ever on. Now we can use that function plot, right, in the xy coordinate plane to go ahead and generate the polar plot. Let's see. Pretend now that my function value represents my magnitude r. So we can now think about our magnitude r as the value of the function in the direction of my x coordinate. So let's go ahead and rotate, right? Let's go ahead and rotate 0 degrees and plot our first point. That's going to correspond to 3 in the 0 direction. So are we 1, 2, 3? So right here. Is that our first point? Now let's go ahead and spin, right? We're going to spin pi over 2 radians, and we're going to plot the magnitude of 5. Can we do that? You bet your boots. 1, 2, 3, 4, 5. Is that right up there? Are we good? Awesome. Just keep spinning. Just keep spinning back at a rotation of pi radians. We're at 3. 1, 2, 3. At 3 pi over 2 radians. Bless you. At 3 pi over 2 radian direction, we're at 1. So here we are. And at 2 pi, we're back at 3. 1, 2, 3. Okay. That does not seem like enough for me, right, to know what that curve looks like. So now we're going to go ahead and add some secondaries. What? Well, let's go ahead and choose a convenient value on the interval 0 to pi over 2, where my sine will reduce nicely, right, if we're trying to do this non-calculator. So what's a convenient angle measure on 0 to pi over 2, where sine would reduce nicely here with this 2?
Pi over 6.
I'm down, Sydney. Let's do pi over 6. So let's go ahead and do pi over 6. And if we did pi over 6, the sine of pi over 6 is 1/2 times 2 is 1, plus the 3 is 4. So I'm going to go in the pi over 6 direction. I'm going to go 4. 1, 2, 3, 4. How's that? That's my horn, no? Great. What would be a convenient value on pi over 2 to pi? Let's go 5 pi over 6. 5 pi over 6. And the sine of 5 pi over 6 is 1/2 also, times 2 is 1, plus 3 is 4. So 1, 2, 3, 4. Bless you.
Thank you.
How's that?
Thanks.
You're welcome.
7 pi over 6. Sine of 7 pi over 6 is negative 1/2 times 2 is negative 1 plus 3 is positive 2. So here we go. 1, 2. And here's our 11 pi over 6. 11 pi over 6, the sine is negative 1/2 times 2 is negative 1 plus the 3 is positive 2 again in the 11 pi over 6 direction. So right here. There we go. And now we start to see it piece together. We could do one tricky point like pi over 4. Pi over 4, the sine of pi over 4 is root 2 over 2, which is about 0.7, times 2 is 1.4, plus 3 is 4.4, so I'm just going to add about 4.4 here. 1, 2, 3, 4.4. We can do the same thing with 3 pi over 4. Again, sine of 3 pi over 4 is root 2 over 2, which is about 0.7. Oh, 7. Times 2 is 1.4, plus the 3 is 4.4, so I'm going for it. 1, 2, 3, 4.4. All right, guys, I think we're ready. Here we go. Shall we? We're spinning and spinning and spinning and continue to choose points in here to see that that's indeed the case. And we had just gotten here with a different, slightly different polar equation at the end of Thursday's class. And the bell rang, pesky bell. So we said, oh, what's that shape? And I said, I love graphing in the polar plane. It turns out that this is called a cardioid. A cardioid, because you can kind of see here that little dimple there, that dimple cardioid. It's a limazon, one of the different kinds of limazons, and we're going to investigate that more today. So I thought that was pretty cool. Awesome. Pretty little graph. Questions about our 3 plus sine, our 2 sine data? Okay. Let's switch gears and get to what we should have. So I just pulled this in from last file, but I did make a new grid for you. So this is the one we didn't get to, the 4 sine of 3x, the 4 sine of 3x. And this one we've got some more transformations going on. And so this time, I'm not going to do our same window, the 0 to 2 pi, because of our period change here. I know that my speed factor, right, my rotation speed factor there is 3. And so to calculate my period of this new graph, I can go ahead and take my regular period, which is 2 pi radians for the sine function, and divide it by my speed factor 3. So it looks like the period of this new graph is 2 pi over 3. So that I can make a convenient plot, I'm going to go ahead and consider the quarter period. The quarter period? Yeah, and then every tick mark I could do my quarter period. So a quarter of 2 pi over 3 looks like it's pi over 6. And all that is so that we can say tick mark, tick mark, tick mark, I'll go by pi over 6. So what I'm doing is I'm taking the period of my regular sine function 2 pi, I'm dividing it by my speed factor b to determine the period of this newly transformed graph. And then I'm going to go ahead and do a quarter period just so that I know where to make my tick marks. In other words, I'm going to go pi over 6. Pi over 3 is 2 pi over 6. No fixing that. No fixing that, Tyler. 3 pi over 6 is pi over 2. And 4 pi over 6 is 2 pi over 3. And there's a full period. What else has changed? My amplitude. So the amplitude on this is 4, right? So it looks to me like my center line at y equals 0, I'm going to go to my max in the first quarter period. I need to go up 4 units. Goodness. So we better go 1, 2, 3, 4, and -1, -2, -3, -4. How's that? We okay? So let's go ahead and make that picture 0, 0. Like the keeper on my club soccer team always said, regardless of what the score was when we started the second half, 0-0. Come on, you guys, 0-0. Like reset. You're not if you're up like reset. 0-0, you guys. All right. Reset. Okay. So let's go ahead and get my max in. There we go. Back to center line. Min. Center line. How do we do? Yes? Okay? All right. That's pretty sweet. How in the world is that picture going to help us make our polar graph, right? Well, again, we'll consider those function values, sine included, as our magnitude r values in the polar coordinate plane. So let's go ahead and get some of those. It looks like at a direction of 0, we're going 0. At a direction of pi over 6, we're going 4. Goodness. So we've got pi over 6 is here. 1, 2, 3, 4. Then at pi over 3, we're back at 0. So it looks like we need something else in here to get from 4, a magnitude of 4, and then all the way back to 0 by pi over 3. So what are we going to do? Well, let's pick something in between here. So what would reduce nicely here, right? If we picked half of pi over 12, let's try pi over 12. Pi over 12 is this little grid line. 3 times pi over 12 is pi over 4. The sine of pi over 4 is root 2 over 2, which is about 0.7. So 0.7 times 4 is about 2.8. Can we do that? 1, 2, so about here, another convenient value would be 1 pi over 12, 2 pi over 12, 3 pi over 12, right? Which is the same as pi over 4. Pi over 4, and for x, 3 pi over 4, the sine of 3 pi over 4 is root 2 over 2, which is about 0.7, times 4 is 2.8. Here we go. We could continue choosing, right, angles that are not grid lines in here, and we generate what appears to be like, oh, I don't know, a petal shape. Where we get kind of this petal. Then we can obviously embellish some the leaf later and some decorations, but now let's keep going with our spinning. So what did we get? We got pi over 12 is right here. Okay, now let's go ahead and consider some negative values. By pi over 2, we need to have a negative r value, negative 4. So in the pi over 2 direction, that's straight up. We're going to go straight down. How many units? 4. How's that?
Perfect.
Okay. What's going to be convenient on that interval? Oh my gosh. So what if we did... So we're going to have 2 pi over 3. We've got to be back to 0. So what would be a good thing to pick on this window? Right around here. Can we pick anything in here? No? Maybe? 5 pi over 12? 5 pi over 12? So 4 pi over 12 is here, 5 pi over 12. 3 times 5 pi over 12 will be 5 pi over 4. The sine of 5 pi over 4 is the negative root 2 over 2. And that's negative 0.7 times 4 is negative 2.8. Can we go in the 5 pi over 12 direction? We're going to go negative 2.8. We can do that. 1, 2.8. Oh, how's that? 6, 7 pi over 12. 7 pi over 12 times 3 is 3 pi over 4. Yes? Did you pick 7 pi over 12? 7 pi over 12 times 3 is, 7 pi over 4. Negative 0.7 times 2. There we go. So here we are, 2.8 again. Now we're going to do our next one. What do you mean our next one? Well, we've done one full cycle. Are we going to gain anything new by completing another cycle on our Cartesian grid? Well, in terms of behavior, no. This is the behavior that's going to repeat. It's just that we've only got to 2 pi over 3, right? Another cycle will get us to 4 pi over 3, and finally to 6 pi over 3 would be a full 2 pi. So if we went for our standard 0 to 2 pi window, we would continue creating these rose curves, but would retrace. For our next interval, we would now get here. 1, 2, 3, 4. Again, 2.8. 2.8. About. Our next cycle would get this, and this again. So we wouldn't add anything new. And our final cycle, 1 and 2. Now, the moment we've been waiting for. No, not for the bell to ring, like last time. Let's go ahead and everybody, let's check out our graphs. And so here we go. let's add in our emulator now. Okay, so everybody, let's go ahead and add in our emulator. You think that's a pretty little graph? I think it's a pretty little graph too. Okay, guys, let's go ahead and practice with our mode then. We got an introduction to this last time. I want to do the last two graphs just to make sure we're doing okay. So everybody, let's go ahead and take a look at our r equals 3 plus 2 sine theta, and I want to see how we did. At this time, everybody, please, let's go to our mode, and let's go to, where's my, so I want radian, that's good, but I want polar. So I want to go here, how about? Hooray, so let's do polar. And now when I go to my y equals menu, it gives me the r, right? It gives me r for my r equals equation. I want to do 3 plus 2 sine theta. And I'm going to go 0 to 2 pi. Let's see if it's already, it already has that as my default with the step appointment. Okay, so let's go ahead and try that. To make this match a little bit better, what do we want for our grid? Let's not go negative 10 to 10. I'm going to just try. I'm going to see what that does. Whoa! Check it out, you guys. We've got a dimple. Beam is on. So what if I do zoom square? Will that help a little bit? Zoom square, the fifth option. Hey, there we go. This is a keeper. This is a screenshot for PDFable right there. Dang. That's pretty good, you guys. All right, go ahead and show your partner when you created this graph on your screen. I want to make sure you're good with the polar. We just did an intro on Thursday. Did you guys make it? And if they don't have it, you may help them. Amazon. It's front. It's front. Okay, you guys. Enough talk. Now we eat. Let's go ahead and take a look at our super duper one. So this one, right? We kind of sped up a little at the end. I think it's useful here to watch trace this out. And so let's go ahead and do y equals. And this time, let's do the function 4 sine 3 theta in my angle input. So we'll try 4 sine, and inside we'll do 3 theta, close. And I want to see this, trace this out. And so I'm going to go ahead and I'm going to go to my line style. Is this just going to do color, or is it going to do line style? I mean, let's do line. Oh! My favorite, the ping pong ball? Sure. Can I okay that? Okay. Ready? Let's do it. Oh, 1, 2, 3, up, repeat, and to get the full thing, you guys see that? Gosh, I want to change something to see if it'll do that again. So, if I type that again, will it do a new one? Yeah, look at that. Dang, how'd we do? This is PDFable. This is our screenshot. There's our screenshot right there. I'm impressed with our work. By golly, that's pretty good. Now, obviously, if I were a real stickler, right, I'd go back and take the time to change this line style to red just so it would super match, but I think the complement there is kind of nice. So that's PDFable enough for a Monday, right? That's pretty cool. So there's different categories of functions, right, in the polar equation, in the polar grid, and today your polar graphing activity, the final one of our Unit 1 prerequisites, is aimed at investigating those. So you will be completing your activity together. Today's stamps include 1, 2, 3, 4 stamps possible, and you can earn those on items 1B, the graph, 4C, and number 9. Okay, so when you guys agree on these, you're going to raise your hand, I'll come over to you, and I'll get you guys stamps all at once. And then we've got our closure slide. We need to make sure we allow a little bit of time for that. And so I think you got a nice chunk. I'll pause the recording. You guys can go ahead and get started. And then we should have an opportunity to start your OTL 5 tonight as well. Thank you, guys. All right, ladies and gentlemen, so let's generalize some of our findings. For today's closure, I asked that you describe the difference in symmetry between polar graphs that are based on the sine function versus those that are based on the cosine function. And I'm going to call on you to share with the whole class. Then, as you finish up the activity, what were some identities that were particularly useful when switching between a polar equation and the Cartesian, that is the rectangular coordinates x and y equation? So that's what you just did for your final 9 stamp, right? What were identities that were particularly useful for that? I'm going to ask you to share that as well. Okay, what was the difference in symmetry for polar equations based on cosine versus sine? Right? So what was the symmetry observed when our polar equation was based on cosine? What does that look like? Grace?
Horizontal symmetry?
Yeah, there's horizontal symmetry. There's symmetric about the x-axis. So we had this x-axis symmetry. And versus the sine function, Vivian? Yeah, there's a vertical kind of left-right fold symmetry or y-axis symmetry. Raise your hand if you had the same observations regarding symmetry. Awesome. And then which identities were useful? So there are a couple that are relationships, right? Which identities were useful? Well, what was one that was useful when you're trying to go back and forth from polar to Cartesian? What was one that was useful? Tyler?
X equals R cosine theta.
Definitely, right? Our x equals r cosine theta, which goes back to our regular right triangle tree, SOHCAHTOA. That's how we developed that. What other relationships were useful? Sophia?
Y equals R times sine.
Yeah, y equals r times sine theta was definitely useful. And big bad mother daddy of them all, right? What was our other relation that was also useful? Kobe? Yeah, Pythagorean theorem, that x squared plus y squared equals r squared, or cosine theta squared plus sine theta squared, right, equals 1. So that Pythagorean theorem was also useful. Or cosine theta squared, right? Cosine squared theta. Awesome work, you guys. I'm going to go ahead and stop the recording, but first, your OTL number 5 includes your OTL number 5 worksheet. It looks like everybody got your photographing activity stamps, so nice job today. Great work.